Good morning. Um, we have worked our way pretty much through chapters 25 and 26. I think it's time to take one of our classes and go back and look at some of the challenging homework problems. So today that's what I'd like to do, is actually go back and it's going to give us a chance. 25 and 26 are kind of related chapters. So I've gone through the homework and looked at some of the examples, and let's work through some of the homework. I want to talk about some of the problems and some of the setups, which is such a big part of these courses, right? And so let's do that. Boy, it's nice to be back in the classroom here. Wait, this isn't the classroom, it's still my garage. Anyway, brought my Laney Physics Club sweatshirt, but it's spring now, so it's pretty warm. So we can put that aside. And we've got our class mascot. Laney the Eagle is visiting today with us. So I think we're ready to get started. So again, I've picked out some questions from chapters 25 and 26 from the homework. And let's talk about some of those. And some of these examples I'm looking at, we're going to make some additions. So we're going to add some things onto some of these problems, make them a little more interesting than the way they're written up. So let's do that. Looks like the first problem we want to take a look at is a homework problem from chapter 25. It's problem 27, and it's a spherical resistor. So, which is kind of interesting, right? I mean, when we've looked at resistors in class, resistors always looked kind of like this. We had a wire coming into each end, and maybe the resistors were kind of cylindrical in shape. And what we understood from resistors is there's some kind of material with a low conductivity or a certain amount of resistance to it, resistivity. And our formula for resistance said it depends on what the material is that we've made it out of. It depends on how long the resistor is, and it depends on the cross-sectional area. Now, for a resistor that's cylindrically shaped, that's not such a big deal. We can just look up what the material it's made out of. That's going to be the resistivity, and then there's going to be some kind of length. So, and then we're dividing through by the cross-sectional area. Now, if we think of going from one end of the resistor to the other, in a cylinder, all of the sections that we pass through are not us, but the current. So the current's passing through these successive sections of the resistor, and they're all the same area. So that's easy enough. If they're all the same area, then we just take the combined length and solve for the resistance this way. But what happens if the area is changing? And that's what's going on with a spherical resistor. So with a spherical resistor, I don't know how they built this, but you know, you guys, when you're out there engineering different devices, you can make a spherical resistor and see if this really works. But it's some kind of hollow sphere. So the sphere's been hollowed out, and instead of taking the wires and attaching them on the ends, which you would do on a typical type of resistor, somehow what we're going to do is we're going to attach a wire to the outer surface and attach a wire to the inner surface, and maybe put a conductive layer right around the sphere here and outside. It's a lot of work to go to, but we're going to do it. We're going to build a spherically shaped resistor. Now, if we think of the current, let's say that the current is traveling from the inside of this sphere, and then it makes its way outward to the outer surface. So for that, we're going to need a couple of radiuses. We're going to say that the inner radius is A, the outer radius is B. Those are good symbols to be using. And then each one of these layers we pass through has a thickness of dr. So over here, if we had divided this up into a bunch of layers, you know, each one we would say is like dx, right? But this time we're going to use r because, well, it's a spherical resistor. And so I'm going to measure from the center out to each successive layer. And the distance out to each successive layer is going to be little r. R is going to be our variable of integration. Yeah, this is looking like an integral problem. And then the thickness of each layer will be dr. So that's the plan here. Now, the big R's here are resistance. So at each layer we pass through, there's going to be a little contribution to the resistance. And it's going to depend on the resistivity of the material. We're going to say the material is uniform, so the resistivity is a constant. Each layer has a thickness dr, and then what's going to happen with the sphere is that the area is changing. So each area that we pass through, each spherical shell, is going to have a cross-sectional area of 4 pi r squared. All right, so that's how we're going to set things up. Now, just to throw a curveball in all this, in the problem they say, oh, don't use the resistivity, use sigma, the conductivity. Well, it's just the inverse. So I'm going to go ahead and solve the whole problem in terms of resistivity, okay? And then I'm going to just switch it at the end. That's the last thing I need right now, is some new symbol that's the inverse of something I've already got. So here we go. Here's the setup. As the current makes its way out through each layer is going to contribute a certain amount of resistance. We're going to call that dr. It's going to be the resistivity times the thickness of the layer divided by the cross-sectional area, which is going to be 4 pi r squared. So this is nice. You know, this is another good example of setting up an integration that's very physics-based. So everything in here means something. Every symbol means something in here, right? This is actually the dimensions of this resistor, and that's its material properties. We need to vary r from the inner radius to the outer radius, and that's going to determine for us our limits of integration. We got to go from r equals a out to r equals b. So that's going to be the plan. And that's it. So the integral is now completely set up. I pulled out the constants. I left the factors of little r inside. And what that integral is going to give me, 1 over r squared, well, the integral of that is negative 1 over r. Yeah, that's it, negative 1 over r. I guess that's the whole story. So here is the 1 over r. Now, as I'm always saying, negative signs, once I start to accumulate negative signs, I start making errors in my calculation. So an easy way to eliminate the negative sign that used to be there is I flip the units. Oh, I flip the limits, sorry. I flip the limits so that I'm integrating from b to a instead of a to b. And flipping the limits of integration will introduce a negative sign. It's going to cancel out the negative sign that was already there. And so this is going to be rho. You guys weren't thinking that was p, right? That's not a Roman p. That is a Greek rho, and it has the sound of r. Yeah, you guys are going to be, you're going to be able to read Greek when we get through. I'm not entirely kidding about that. Take a look at look up some Greek writing and see if you can sound out kind of some of those letters that are there. Anyway, that's an r sound. Rho over 4 pi. And if I follow my integration limits here, that's 1 over a minus 1 over b. And that's it. That's the formula. Oh, wait. They wanted us to do this in terms of conductivity. So I took out the rho and put in sigma. Done. Right? And then I simplified the expression. Remember, simplifying the expression is a really important part of the problem. Okay, if we get it into a simpler form, a lot of times the formula, we can see things in the formula that will tell us, well, what it's going to depend on. So, so that's it. Questions on that? That's a good problem to start off with. So again, it's a chapter 25 problem. It's a good chance to go back and take a look at a problem from a previous chapter. All right, let's move on. Let's look at problem 39, chapter 25. This is the toaster problem, and toasters are simple enough devices. I mean, if you think about what a toaster is, it's a heating element, right? If you look down inside, don't stick a knife down in there. If you look down inside the toaster, there's a little wire in there that heats up And so it's easy enough to see where the energy is going. So for our toaster, wow, it says it's 550 watts. That's a good amount of power for this appliance. So that's a medium-sized power usage. You know, a microwave oven might be 1,000 or 1,200 watts or something like that. So this toaster, you know, it's like half a microwave oven. It says that this toaster takes 6 minutes. Now, I don't know what the setting here is. I don't know if that's, you know, really crispy toast or what. 6 minutes sounds like a long time. Anyway, the 6 minutes, I converted into seconds because minutes aren't standard units. And then I also converted it into hours. And you know, the reason I converted it into hours is because there are these units, kilowatt hours, that, for better or worse, are pretty common units. Now, I'm kind of, you know, I can work in kilowatt hours or not. I feel like everything should be converted to joules, but there is so much stuff in kilowatt hours that I'm going to go ahead and say, yeah, let's go ahead and see how this is going to work. So I calculated the energy. Now, the energy we can get by taking power, remember P is power here, times time, and I did it two different ways. I did it as 550 watts times 1/10 of an hour. That's what the 6 minutes is. And what that gave me was 55.0 watt hours. Well, a watt hour is kind of sounds like a kilowatt hour. There's got to be a factor of 1,000 in there. So we got to divide through by 1,000, and that gives us 0.0550 kilowatt hours. So it's this, you know, it's a tiny fraction, but hey, it's a toaster. It's only on for 6 minutes, right? How much energy is that going to use? I also calculated it in joules. So 550 watts, standard units, 360 seconds, standard units, 198,000 joules, and I do like using joules for everything, I guess, so that you can do easy comparisons. What about the cost? Now, the cost for this, they tell us, is 9 cents per kilowatt hour. Now, you know, they could have given this to us in joules also. It's not like the cost of electricity has to be in kilowatt hours. But I'm going to go along with that. So 9 cents per kilowatt hour. So I took that conversion factor and set it up in a way where the kilowatt hours will cancel out. So don't lose track of units, you know, on these problems. That's going to be important. And it worked out to be each day or each instance of, you know, each 6 minute toasting that takes place is going to be 0.495 cents is what I ended up with. Okay, so good to know. When I toast my toast in the morning, I guess, with this toaster, it's going to cost ½ cent. Except that electricity here, if you look at your PG&E bill, it's not 9 cents per kilowatt hour. This is probably off in, I don't know, maybe it's off in Texas somewhere where they keep the, I don't know. Anyway, electricity here is more expensive. Electricity here is probably 2 to 3 times more expensive. It's probably more like 20 or 25 cents per kilowatt hour. So that would bump this up, right, to over 1 cent for the toast. Okay, so very good. Now, electricity costs are going up, but we do want to switch over to electricity. We want to eliminate natural gas usage, so we stop putting greenhouse gases, carbon dioxide, into the atmosphere. So what we want to do is just ramp up that electricity production as a way to make sure that we have electricity here. And I don't know if there's any natural gas toasters out there. I think they're all electric. All right, now, it said this in the problem. It said that we actually make toast four times a week. And I wanted to know what days. Okay, if it's 4 times a week, which days are we making toast? And they didn't say. So I guess there's just some kind of a quota system. You got to make toast 4 times a week. And so that, for a week, you know, it came up to 1.98 cents or 2 cents, at least at this electricity cost, at this rate. That bumped that up to about 2 cents a week. Ooh, and then here is the very, very hardest part of the whole problem. It said how much would that cost each month? And I don't know. It depends on which month, right? February has 28 days, March has 31. How many times are we? I can't believe they actually asked per month and forced us to make some kind of an estimate there. Let's see, we'll just throw, this is like 2 cents a week, and a month, I don't know, if it's like four weeks and a few more days, I don't know, it's going to be like 4 times, so it's going to be, 8.5 cents, something like that. That's so it's just an estimate here. Now, I wanted to point out on this problem, I mean, this toaster, more likely than not, this is getting plugged into an outlet. So I just want to review the stuff we learned back in chapter 25 on AC electricity. So alternating current, which is what our outlets run off of, that 550 watts is actually an average power. What we saw back in chapter 25 is that the power rises and falls 60 times a second. It actually goes 120 times a second that it cycles through. So the peak power would actually be 1100 watts, and then the average power would be 1/2 of that. So just a reminder, and then if we're plugging into a standard outlet, if it's a toaster going into a standard outlet, that outlet is going to be at 120 volts, but the 120 volt is an RMS number. So that's RMS, that's also averaged. The peak voltage would be larger by a square root of 2. So you should know your way around all these conversions between peak values and averages and RMSs. If not, go back to chapter 25, practice the examples from those lectures there. And then also the current. So I solved for the current. The current we can get by taking the power and dividing through by the voltage, and that gave us, it's voltage divided by, power divided by voltage, that's right. So we got the power divided by the voltage, and that gave me 4.58 amps. So again, that's kind of a medium range appliance, right? That's not small. That's not the a light on my nightstand or a clock on my nightstand or something. 4.6 amps, and then the peak value on the current would be 6.58. All right, there it is, the toaster problem. Beware of counting how many weeks there are in a month. All right, here we go. One more problem here, one after another. Problem 2545. So I get a lot of questions on this also. This is I feel like it's a pretty tricky problem. So what we've got going on here is there's a power station and there's a factory. And the power station, the power plant, is supplying the factory with electricity, with electrical energy. Now, between the power station and the factory are a bunch of wires. These high voltage wires up on these high voltage wire towers, getting the electricity to go, or the energy to get transferred between power station and factory. Now, it says that the wires, all the way from the station to the factory, and there's there's a set of wires here. So we got to think in terms of 2 wires. Combined resistance is 3.0 ohms. So the wires are going to be thick enough. I don't know, what are high voltage wires made out of? Are they like steel or something? Because they got to be strong. I can't imagine they would be made out of copper. Anyway, we got 3 ohms of resistance total right here. Now, they gave us some numbers, and I wasn't sure whether to apply those to the power station or the factory, so I went ahead and focused on the factory. It sounded kind of like in the problem that they were looking for is what's going on at the factory. So apparently the factory is planning or expecting that it's going to be using 750 kilowatts. Okay, so that's a good amount of power, 750,000 watts. And it's intending that the electricity is supplied at 12,000 volts. All right, so that's a really high voltage that they're operating at. So they're going to have, you know, again, they're going to have high voltage towers and stuff to protect people from this 12,000 volt line, make sure that it's not just necessarily running through neighborhoods. Now, what they want us to find out in the problem is how much energy is going to get lost. Now, when they talk about energy loss, they're thinking about the wires. So the energy loss is taking place as a result of the resistance in the wires. And now, to calculate the power of any of these items, the factory or what we can do is, if it's got resistance, we saw three different formulas for this. We said power could be calculated as V times I, V squared over R, or R times I squared. Now, in this particular example, we want to use I times I squared. And the reason why is this: they've told us the resistance, so I know that. I don't know the voltage across the wires. And you're thinking, well, wait, isn't that the 12,000 volts? And you go, no, that's not it. So what's happening here is there's a power station, there's a set of resistors here. We could think of a factory as another set of resistors. And the voltage across, you know, the resistance in the factory is 12,000 volts. But we don't want that 12,000 volts to be lost in the wiring. So what we've done is we've used the power and the voltage of the factory, and then from that we can get the current. If the factory is, you know, using 750,000 watts and it's being supplied at 12,000 volts, I can calculate the current as P over V, and that says that the total current passing through my power station is 62.5 amps. So you're thinking, that's not a terribly large amount of current. And you're right, you know, for an entire factory, you would think, well, that's not so much current, but we don't need that much current because we're operating at really, really high voltage. Okay, so the current can be low because the voltage is so high, and we can still end up with a lot of energy, a lot of power being transferred. Well, once we've established what the current is in the factory, that value of current applies to the wires. And that's why when we're looking at how much of the wires heating up, we can say that the power then, the heat loss, this is thermal energy being generated in the wires. It's purely due to the resistance in the wires. I'm going to put in my 3 ohms, and I can put in my 62.5 amps. So we need to understand that the wires are in series with the factory. And so the wires and the factory will be operating at the same current. Okay? This is where, you know, you really have to understand conceptually what's going on kind of throughout physics. And again, I mean, I've said this before, that often students are saying, well, if you just know the formulas, you're fine. But it's not enough. You really need to understand conceptually what's going on so that you can, formulas are great. You can pull out the right formula and put all of the correct information into that. So this is the formula you want to work with. We've talked about why we're using that and plugged everything in carefully. It looks like the wires are going to lose 11,720 watts due to heating. Now, the factory is, receiving 750,000 watts, 11,720 watts, well, that's 1.5%. So it's not like it's a huge portion of the energy that's going into heating the wires, but maybe we could do better, right? Maybe we could recover some of this 1.5% that we have right here. So in addition to the wire heating, which we calculated here, the power, the rate of thermal energy loss, I also calculated how much of the voltage. I was kind of concerned about this 12,000 volts of the factory because the power station voltage is going to have to be higher because again, the wires in the factory are in series, and that says we're going to have some voltage loss with the wires. The wires are going to have a voltage across them. And so I calculated the voltage across the wires. Well, it was, 180 volts, 190 volts. So out of 12,000 volts, that's a pretty small number. Okay, that's looking like, 1.5% of the voltage is lost during the transmit of the electrical energy. Now remember, another thing you have to keep track of here is, so when you're visualizing all this, current is actually not doing this. Current is not steadily going in this direction. And then current goes through the factory, and then current has this other wire here. This is AC. And so what's happening is there's a steady set of electrons all through the wiring in the generators in the power plant. Those electrons are all throughout both wires. The electrons are in all the wiring in the factory. And because it's AC, those generators are pushing the electrons back and forth 60 times a second. So the electrons don't go anywhere, right? We've got all of these electrons lined up through all this wiring through the factory, and we actually transmit energy by having the generator here push the electrons back and forth. So the electrons are getting pushed back and forth here. That means in the wires they're going back and forth. We could go back and use some of those formulas from those I didn't do this. But that last section in chapter 25, when we were looking at the details of copper wiring, and you could actually measure how far back and forth the electrons are traveling as they oscillate. So the electrons are just oscillating, and that energy gets transferred to the power factory, because now the wiring inside here, the electrons are moving back and forth. And electrons moving back and forth can be used to generate heat. They can be used to make motors turn around. Okay, so you can get mechanical energy out or thermal energy out by letting these electrons oscillate back and forth in the wiring. All right, the later part of the problem, what they ask us to do is to increase the voltage. Instead of 12,000 volts, would we be doing even better at 50,000 volts? Now, at 50,000 volts, I guess it's a bigger risk, but at 50,000 volts, if this is, again, these are factory numbers, so if I have 50,000 volts at the factory, I can take that same amount of power, the 750,000 watts, and divide through by the voltage, and the current it says we need now is only 15 amps. So before, at 12,000 volts, we needed 62 amps. But now we're only going to need 15 amps. So, the current requirements have dropped because we boosted the voltage. Okay. Now when we do the wire calculations, we look to see how much thermal energy, what's the rate at which thermal energy is being generated in the wire. That's R times I squared. Ooh, it's down to 675 watts. That's a lot, right? So we reduced the current by a factor of 4 or more than 4, a little more than 4. And so this is going to reduce down by a factor of 16 or more, and that's where it leaves us. So we're down to 675 watts, 0.090%, now less than 0.1% now of the energy is being lost because we ran everything at 50,000 volts instead of at 12,000 volts. And the wiring, the wires that we're going to use here don't necessarily have to be, they don't have to withstand all of this heating, they just have to be able to withstand this much heating. So maybe we save on some wiring too. I am not sure about that detail. All right, and then as far as the voltage lost in the wires, it's down to only 45 volts. So compared with the 50,000 volts that we're operating at, 45 volts is just, a little uncertainty in what the voltage is operating at. All right, so you can see the effects of going to really high voltages and how they are going to be able to save energy of the wire heating. Let's move on, and you guys have questions, let me know. But let's take a look at problem 49. Problem 49, still in chapter 25. Now this is a full-blown alternating current AC problem. And it's a pretty straightforward one, I hope. It says we have an AC generator, and we're just going to have one device with a resistance of 2,700 ohms. So I got one resistor in that circuit. And it tells us here that it's not a standard 120 outlet that we're plugging into here. We're actually plugging into a 220 volt. So maybe this is standard in Europe, for example, of 220 volts. Now, I put this little chart here because, again, you guys should know your way back and forth between peak values and averages for alternating current. Now, alternating current, as we said in chapter 25, the generators generate this, so it's a pure sine or cosine function. And so for that, we can do a root mean square averaging. And for a sine or a cosine function, the root mean square value is the square root of 1/2 times the peak voltage, which works out to be, what is it, like 71%, 70.7, something like that. For the average power, that's going to work out 1/2 of the peak. So let's see what they gave us in the problem. So in the problem, they told us the resistance. They told us an RMS voltage. Now the easiest thing to calculate from that, I guess, is the current RMS. And the current RMS is 81.5 milliamps. Now they're asking us about what is the peak current, which is fine, but I always feel like on these homework problems, I might as well get some practice just filling in everything. So it's kind of like practice using this whole set of formulas and relationships. And so they gave us this, the RMS voltage, and they gave us the resistance, so we were able to calculate the RMS current. Now I can multiply those, I guess I have to switch this around. I can multiply these RMS values by a square root of 2. If I multiply those by a square root of 2, that's going to put me back with peak values. So this jumps up to 115, and this goes up to 311 volts and 115 milliamps. We are in milliamps, huh? Yeah, it's a pretty large resistance. And then as far as the power we can get by taking I times V. So power is equal to V times I, and if I'm using the RMS values, that works out to be an average power of 18. So if I just take V times I, and I stay with this row of average and RMS values, I ended up with 18 watts. If I multiply these values together, the peak values, then it's 36. So what's happening in terms of power? Now, power doesn't go negative. So if all I have in a circuit is a resistor, and the current's oscillating back and forth, well, when the current rises, the power goes up. But when the current drops, the power goes back down. If the current reverses direction, which it does in alternating current, it really doesn't make any difference in terms of the power. If the current's traveling this direction compared with this direction, it's still going to come down to a positive amount of power. Now, by positive amount of power, that means we're going to be generating thermal energy in that device. The resistor is going to be taking electrical energy, converting it into thermal energy, and that's independent of which direction the current is traveling. So the power varies from 0 to 36. So the power is, going between 0 up to as much as 36, and then it oscillates back and forth between those numbers, and on average it's right in the middle at 18. So that's the easy one, right? The average power is just half of the peak. Okay, so know your way around all of those conversions. Ooh, all right. We are into chapter 26 here, and it's a resistor network. And let's take a look. So in chapter 26, we've been looking at, circuits that look something like this, right? Or something like this, or something like this. Now, this was the original circuit given in the problem. It says we have a battery, and we have a resistor 1 here, and then we have 3 separate branches. Now, to me, those look like they're in parallel, and then these combined, once I get these combined, they are in series with R1. So I'm going to redraw them. Now, whatever's your favorite way to redraw them, if you see the problem and you don't need to redraw it, that's fine too. But I almost always in these problems just practice, in some sense, redrawing these and go, how can I redraw that so that it's more immediate, I can see what's going on. I tend to go from top to bottom. So I got the positive plate here on the battery. Let's bring the wire around, and the first resistor we encounter is R1 when we do a walk around. So we first of all encounter R1, and then R1 comes up and splits into resistor 3, a path through resistor 3 and a path through resistor 4. Now, they want us to solve this problem with the switch open and then resolve it with the switch closed. Or at least I'm going to solve it that way, because that's what they're really asking. Now, so I drew both of these. Here is one where the switch is open, and there's just 2 resistors at this stage. And then once we close the switch, now we got a 3rd resistor. Now, in this problem, what they initially say is we're not giving you any numbers. Don't carry out any algebra. Just reason through this from your experience in working with resistors, and tell us when we go from here to here, when we close that switch, is the overall, are the voltages going to go up or down? Are the currents going to go up and down in the individual resistors? Some may go up, some may go down. And what happens to the overall power usage in the circuit? So let's think about this. If I go from this picture to this picture, where there used to be 2 resistors in parallel, there are now 3 resistors in parallel. Now, if we think back to what we learned in chapter 26, what we've been talking about, if I add more paths for the current, if I add another path where the current can travel, that lowers the overall resistance. So the first thing I want to write down for part A is, hey, the resistance with 2, 3, and 4 all in place is now less than the resistance used to be when there were just 2 resistors there. So adding a resistor in parallel will always reduce the overall resistance in that section. Now, if this section has lower overall resistance, then what I can do is I can combine that with R1 and say those are in series, and the resistances then would come from taking R2, 3, 4 and adding on R1. Here I'd be taking R3, 4 and adding on R1. Well, if 2, 3, 4 is less than R3, 4, then 1, 2, 3, 4 is less than 1, 3, 4. So it says that overall, by adding that resistor in parallel at that one location, overall the resistance for the whole network is going to go down. And that doesn't matter what the values are for R1, R2, R3, and R4. It's independent. No matter what the values are for those 4 resistors, the overall resistance will decrease. And so, yeah, it's good conceptual, practice, thinking about what would happen in this case. Now, if the overall resistance goes down here and it's higher here, that means that now I can think of this as just one resistor here and compare it with one resistor here. Well, this resistor has more resistance than that one does, once we've done the equivalent resistance approach. And so this is going to have less current, and this will now have more current. So the current, now I've called it I1, but it's really just the total current through the whole network. So if I look at the current through that whole network, I1 has increased when we close that switch. Now if I1 has increased the current through R1, that means that the voltage here has also increased. The voltage will always be given by R times I, V equals R times I, for any individual resistor. So if the current goes up, that means I1 went up, V1 increased. Now, if I look at this circuit here, I've got a certain amount of voltage available from the battery. And when I draw them like this, I can say some of that voltage will be here, and the rest of the voltage will be here across this combination of resistors. So those two numbers combined, they have to add up to the total voltage, right? If I get my voltmeter out and start measuring, and I do a voltage reading here and a voltage reading here, those two readings combined, it's direct current. Those two readings combined will add up to the voltage of the battery. We'll find out with alternating currents and combining resistors and capacitors. It's not necessarily the case. It's not as simple as just adding voltages, but with DC it is. So I can take this number, add that number, I'll get the overall. So if this voltage has gone up here, well then the voltage here has gone down because it's a fixed total amount. It's a zero-sum game. So this voltage goes up, this voltage goes down. That means V3 and V4 have decreased. Now if those have decreased, what we've established was that I1 has increased. Well, I3 and I4 are going to decrease. There is less voltage now. Up here, there was more voltage across these two. Down here, there's less voltage across these two. Now, what's going on here is we don't need as much voltage in the bottom section anymore because we've introduced a third path. So if I look at the current in R2, even though the currents in 3 and 4 have gone down, when I combine 3, 4, and then this new addition of resistor 2, the current overall has gone up in that section. So in part C, I has increased overall in the circuit. V is a constant. The battery is still operating at the same voltage. It's still running the same chemical reaction. And so power has gone up. The battery's using up its energy at a faster rate when we close that switch with a resistor that was in parallel. Okay. So that's, I'm going to say that's pretty impressive. That's a lot that we were able to say about this circuit without putting any numbers in, without really doing any algebra. We didn't write down any equations. We did make use of our what we've learned as far as resistors in parallel and resistors in series. So that we definitely used that in solving the problem. Now in this particular homework problem, this is part A, B, and C. In part D, they actually give you some numbers for these resistors, and they have you go in and solve that one, and go in and solve that one, and check to see if all of the predictions were correct. Okay, so these should be the correct predictions. Go ahead and do that. Fill that in. I'm not going to do that right now. I'm not going to go through that in today's class because it takes a fair amount of time, and I feel like you guys can do that. But make sure that you can set up, you can solve resistor networks. Okay, resistor networks, they're out there. They're going to show up on a midterm or a final exam or something. All right, moving on, still in chapter 26, battery and resistors. This just looks scary, right? This really has a lot of stuff going on here. Now, this was a circuit that they gave us, and I drew it out. So I have to sort out some stuff here. Here's a battery here. Here's a battery here. They have a certain orientation to them. They've also told us that they're going to define the current going through that branch as I1, current here is I2, current here is I3. So I redraw this. You know, I always end up redrawing these. Once the circuits get to a certain level of complexity, I end up redrawing it, sometimes a couple times. So I redrew it here with my definitions of current directions, 1, 2, and 3. And I even wrote down a current expression saying that, look, if I have currents 1 and 2 coming into point D and current 3 is leaving, it must be that current 3's value is the combined value of current 1 and current 2. So that's an equation I can write down using a junction statement. Now, what I also noticed is that they've got multiple resistors along each branch. Like here's a 1 and here's an 18. Well, that could be turned into 19. And I've got a, well, this is just 34. But here I got 47 and 1. That could be turned into a 48. And then these batteries, oh my gosh, they're 45 volt batteries and 75 volt batteries. Okay, so they're fairly high voltage batteries that we're operating with here. So I redrew it. I redo it this way. To me, putting the batteries kind of in the same part of the loops. So now what I can see is I've got these 3 branches. I've got a battery in 2 of the branches. I'm calling this V3 and this V2. I'm calling this was current 3. And so everything on this branch I'm labeling 3, everything here I'm labeling 2, everything here I'm labeling 1. And some of this, I didn't really end up using these symbols so much, but what I am going to do is I'm going to come back and do a couple of loop equations. Now for my loop equations, I'm going to start with this loop in that upper region, and then I'm going to go to this loop in the lower region. And what I'm going to do is I'm going to follow the directions that they gave me in the problem, and just stick with the convention that they have set up. So in a loop equation, what we can do is look at all the voltage boosts and set those equal to all the voltage drops. So write that down. Voltage boosts in a circuit will equal all the voltage drops. And as long as I'm following the current direction, all the resistors will be voltage drops. So in that upper loop, I have just this one battery, and that battery was my voltage boost, and that was 45. And then I had 2 resistances. I had to deal with R1 and R3. Now the current going through R1 is I1, but the current going through R3 is I3. So what this is R1, the 34 ohms, times I1 plus 48 times I3. Now, we can do the same thing with the lower loop. With the lower loop, I have 2 batteries, and it turns out that the 2 batteries are working together. And what I mean by that is they're moving the current in the same direction. So I can take the 45 volts here and the 75 volts here, combined. That gives me a voltage boost of 120 volts. Those are my 2 batteries. There's 19 ohms of resistance along the path where current 2 is traveling, and there's 48 ohms. So this term matches up because they both loops go through the middle branch. Now, what we can do then is we can take these current equations, the I3 is equal to I1 plus I2, and substitute those in. I substituted them in for I3. And so what that did was it eliminated I3 from my equations. I had started out with 3 equations and 3 unknowns, and now we're down to 2 equations and 2 unknowns because the I3s are gone. Now, there are different techniques for solving these equations. Kind of a basic technique that you likely learned in an algebra class at some point was, you know, I have 2 equations with 2 unknowns like this. I can look at the coefficients in front of, let's say, I2. It's got a 48 coefficient here and a 67 here. Well, if I take this entire upper equation, multiply by 67, and the lower one, and multiply by 48, that would give me coefficients here that match. And so I can multiply these entire equations by these numbers and then subtract the equations. Now, what that would do is it would give me 67 times 45 minus 48 times, those are times, they're not decimals, they're multiplications. And then the I2s will cancel out. That was the intention of setting up these coefficients, was to get the I2s to completely drop out. And so that's what we'll be able to do. And that says that, well, I carried out the calculations here. And that turned out to be 67 times 82 minus 48 times 48. So I got minus 2,745 equals 303,198 times I1. And it turns out I1 is negative 2,745 over 31, it's here. So I calculated that. I1 is minus 0.861 amps. Now, a couple things to point out with the answer here. First of all, in a lot of problems, if you look at the examples in the book, often they will give you easy numbers to work with, so you're not dealing with all these decimals, but the bottom line is this is more realistic. So this is a more realistic problem where I've got to write down these decimals and I've got to keep them all straight. So this did work out to be negative 0.861. It didn't work out to be 1 amp or 2 amps or 2.5 amps. It was this decimal number that I had to keep track of. Now the other thing we should point out here is this turned out to be negative. What does that mean? And it means that the direction that we picked for I1 is actually, the current's actually traveling opposite that. So what we could do is we could change the direction. We could change I1 and say, you know, I1's actually going this way. And then change the sign here. But I'm just going to leave it as is because they define I1 and I2 and I3, and I'm going to stick with what they have done here. So anyway, that's what we came up with. Now, I can also go back and reverse these, pick some different numbers, pick the 82 and the 48. I did that, and for I2 I got 2.408 amps, and then I3, remember, was the combined total. So what this is telling us is, the way I'm going to interpret this, I guess, is that 75 volt battery is driving current. Well, this battery is helping out. So we do have current traveling in this direction with the two batteries, but the 75 volt battery is actually, you know, bigger than the 45 volt battery. It's driving current through this also. And so those are the numbers. We ended up with all of the currents. Okay, and then in the later part of the problem, they go, well, let's go in and determine what are all the voltages. What are the voltages that we're working with in here? So I went back and they wrote down, you know, all these A, B, C, D, E, F. Where did G go? Did I lose track of G? G's at the corner. I did lose track of G. So G is, wait a minute. G is the same as A, right? So they really didn't need both of those. If I've copied this down correctly, we didn't need to keep both. Anyway, apparently G is over here, but it's the same as A. This is A, this is A, this is A, because there's no, that's a direct connection. Those are all at the same voltage. So what you can do is you can follow these different paths. Now, what we could do, what they wanted us to do, was find out the voltage difference between here and here. So I actually started at point D, and I started at the negative terminal. That's a common place to start counting voltage. And so if point D is defined as being 0 volts, then at point C the voltage is going to be 45, and the reason here is batteries are easy. The batteries just tell us how much the voltage will increase from one terminal to the other, and it's going to be higher by definition at the positive plate. So this is 0 and this is 45. Now the key thing here is that there's a 45 volt difference, and just in terms of definition, this is at what we would consider the higher voltage, and this is at the lower voltage. Anyway, 45 volt difference. Now, I took each one of the individual resistors and said the current's going this way, so that's going to be a voltage drop, and this will be an additional voltage drop. And I was able to calculate how much we're going to drop from that 45. We're going to drop by 1.547, and then the second resistor is going to drop by 72.71, and that actually took us to negative 29.25. So that took us down so that the voltage at A is lower than the voltage at D, and it's lower by 29.25. Now, just for comparison, we could pick one of the other paths. And so what I did is I came back, I started here, and instead of going back through the middle, I went around this path to see what the voltages should add up to. Now, if we've done everything correctly, the voltage is a better match. So I started at point A. I set a new 0 point. I'm allowed to do that. And then what I saw was, well, first of all, I'm going to pass through this battery. That battery is going to give me a boost of 75 volts. So by the time I get to point F, I am at 75 volts. And then I also had a couple of voltage drops due to these two resistors. And the voltage drops were 2.4 and 43.3. And that left me at 29.25. So compare, and it worked. Both paths agree that D is at the higher voltage than A, and it's higher by 29.25 volts. I kept too many sig figs, I know, but I didn't want rounding to become an issue, so I put an extra sig fig or two in there. Anyway, that's, good exercise. Go through and keep track of all of the voltages. All right, I think we got a couple more examples here. I think we'll squeeze these in. I think we're pretty much on schedule. I know I'm going through these fast, so any questions, let me know on any of these problems. I hope this is useful to kind of sit down and think. First of all, I'm just looking at this right now. That says V is equal to 12 volts. It does not say RV. It says 12 volts. I apologize for that possible confusion. This was an interesting problem because it says we have a battery, we have two resistors. It didn't show you the diagram. You had to draw it yourself. But it said we had a battery, we had two resistors, two capacitors, everything's in series. So, so I drew it, and it's an RC circuit. RC series? RC circuit, I think is what I meant to say. So this is an RC circuit problem. RC series. Not sure what that means. I'll get that changed. R1 and R2 are both 2200 ohms. Well, I know how to add these together. I'm just going to merge those together into one resistor, and that resistor is going to have a resistance R of 4400 ohms. Now, the two capacitors, they're in series. They can also be merged. 3.80. Now, with everything in series, it also doesn't matter what order these resistors and capacitors are in. The two capacitors don't have to be next to each other to be able to be combined. The resistors don't have to be right next to each other. We could alternate resistor, capacitor. They're still in series with each other, so they could still be combined. We know that for the capacitor, the formula is a little different. It's 1 over and 1 over, and we got to take an inverse. And that worked out to be 1.90. So I got the R, I got the C, and at that point, I can see that what we have is an RC circuit. English is funny. Sometimes you spell things funny. That's pronounced circuit. So it's an RC circuit, and in series, that's what I was saying. It's an RC circuit, and the resistor and the capacitor are in series. All right, and that's got to be the case because that's the only example we've looked at. We haven't looked at examples with R and C that were parallel, for example. So unless we can get this circuit to reduce down to where it's one resistance and one capacitance in series with one voltage source, that's the only thing we've really solved for. And fortunately, we can do that. So here's my R, here's my C. Now the time constant then is given by RC, and that worked out to be 8.36 milliseconds. Now what they wanted us to calculate in here was how long will it take when I close this circuit, how long will it take for the current to drop to 1.50 milliamps? Now I got to find out what the current's going to start off at. So we've looked at these RC circuits, and what we know is if I have a battery in place and I close the switch, the current starts off really high, and then as the capacitors charge, the current drops off and eventually everything shuts down. Because once the capacitors are at full capacitance, so what that really means is once all the voltage is across the capacitors, things aren't going to, the current's not going to flow anymore. Things are going to stop operating. And so the formulas that we had derived in class for this, the current is I naught, and there is that exponential drop off. Now I can flip that around and solve for the exponential factor. That's I naught over I. And then finally the amount of time it takes to go from starting current, which is V over R, that's 2.73, divided by kind of the target current that we're looking for. I can use this formula. So I've derived it right here, and we saw this in other lectures. So what I can do is plug the numbers in. 2.73 over 1.5, the units cancel out, so the milliamps work fine. And then for the time constant, I can plug in that 8.36. All right. So that's what's going on here. We put everything in, and a bit of a coincidence, the time worked out to be 5.00 milliseconds. All right, that's the time, and that's what they wanted. Now, you know, whenever I'm looking at an RC circuit like this, I'm thinking current and charge. What's happening to each one? Now, what we could do is we could ask ourselves for this setup, what would be the full charge? You know, if I have a battery with 12 volts, how much charge eventually will be on this capacitor? And it works out to be, I can calculate that as C times V, and that's 22.8 microcoulombs. And that is going to be true for each of these because they're in series. They were charged together. We combine the two capacitors in series to get an equivalent capacitance, but individually they will acquire that much charge. So this also is going to represent kind of each one of the individual capacitors. Q is equal to Q naught 1 minus e to the minus t over tau. So this is that exponential thing. This function is the complement. These two go together, I guess. The current has dropped down to 55%, carrying out the calculation, going from 2.73 down to 1.50. You know what that means for the charge? The charge will have risen to that complementary value of 45%. And putting all the numbers in, that is what it worked out to be. Okay. So a good problem. And remember, if you're doing a homework problem or if you're on a midterm or a final, you have to be able to get these circuits to where there's a resistance and a capacitance in series with the power supply in order to use the formulas that we've done here. Now I think this is our last example, or the last example that I looked at. This is problem 51 from chapter 26. And what we've got going on here is resistors and capacitors, but what we're going to quickly find out is it's not an RC circuit where we can use our RC charging and discharging formulas. That's not what's going on here. Instead, what's going on is I have a battery. I have one branch. Now the voltage here is 24 volts. Everything over there, those are all the numbers. I got a 24 volt battery, and that means that I got 24 volts across these two resistors. Those two resistors will be sharing the 24 volts. So I looked at the current. I said the current going through the resistors depends on the voltage divided by the total resistance. These resistors are in series, and so I calculated it this way. So here is what the current would be equal to. Now, at some point I decided I wanted to see if I could do the whole thing algebraically, so I did. So I went through and solved for for each one of the individual resistors, what's the voltage, and so I took the current's going to be the same in each of these, so I plugged that expression in and simplified. Oh, I guess that's it. So the voltage across resistor 1 is R1 over R1 plus R2 times the total voltage. For resistor 2, it's an R2 on top. Now that's called a voltage divider. So something that takes a certain amount of voltage and divides it up into two sections, we refer to as a voltage divider. And going along with the equations we have here, it says that the voltage divided up with 16 volts in this across this resistor and 8 volts here. Now they said to take the negative terminal, again the same convention we worked with before, take the negative terminal of the battery and set that equal to 0. That becomes a reference. So if that's a reference, and then this plate would be at 24, let's go see what we've got here. This is at 0, this is at 24. Now, since the voltage across resistor 2 is 8 volts, point A would be at 8 volts. So we're going to designate this as 0 volts, this is 8, this is 24. Now the important numbers here are what's the delta V here, and the delta V here is 8, and the delta V here is 16. Now we do the same thing with the capacitors. Now the capacitors combine differently. So I've got these two resistors, and they're getting the full attention of the battery. Well, these two capacitors are too, because there's 24 volts across these two capacitors. Now, when they charge, they're going to end up with the very same amount of charge on each one. So Q3 is going to match Q4 with the switch open. So I'm just going to call it Q. And what we can do is we can get an equivalent capacitance and say that the charge on each one of these, I'm just going to call that Q, is the equivalent capacitance times the total voltage. So I'm treating this as one capacitor now. And then I can use kind of the same algebraic techniques I did there. I can say the voltage across each one, voltage across capacitor 3, for example, is Q3 over C3. Voltage across capacitor 4, Q4 over C4. And then I carried out the algebra, and what I ended up with were these two equations, which again, these are voltage divider equations. Not only are the two resistors dividing up the 24 volts, the two capacitors in their branch are also dividing up the total 24 volts. Each branch has 24 volts to it. So I carried out the numbers, and the voltage across capacitor 3 is 10.3, and the numbers were a little more complicated, but that's fine. This was 10.3, and this was the lower capacitor, 13.7. So again, following a convention, if I say this is 0, then this would be, what was V4? 13.7, and then this would be an additional 10.3, that would put us at 24. Now in the second part of the problem, there's always a second part of the problem on these, they close the switch. So what happens when we close the switch? Well, before we close the switch, remember how Q3 was equal to Q4? Well, that's not going to be the case anymore, because by closing the switch, B now is going to be at the same voltage as A. So the resistors had set the voltage at point A as 8 volts, and now B is going to be at that very same voltage. Okay, so that means that there's 8 volts across capacitor 4 and 16 volts across capacitor 3. The voltages aren't going to be the, well, what did we have on the previous page? They're not going to be at 10.3 volts and 13.7. They're going to, capacitors now are going to be at the voltages of 8 and 16. Q3 and Q4 aren't going to equal each other anymore. So we can go through and calculate with these new voltages, how are the charges on the capacitors going to change? And what we found, what was the Q from before? Do I have to go back to the previous page? Or maybe I do. The charge we had before, Q was equal to... Oh no, I never solved for Q. I never solved for I. I mean, they didn't ask us to, but usually I'm curious. Okay, I gotta go back and solve for Q, see what that was. I wanted to see how much it had changed. No, I don't see it. Okay, anyway, so here was, what they asked was, when we close the switch, how much charge, this negative plate here and this positive plate here, they used to balance. So it used to be that this plate had negative Q3 on it, and this plate had positive Q4, and since, before we close the switch, since these had the same charge, they combined to be 0. There was no net charge between those two inner plates. So the inside plates, these two, balanced out. Well, they're not going to do that anymore because Q3, with this new voltage, is at 7.68, Q4 is at 2.88. So again, looking specifically at these plates right here, because they want to know what happens, how much of this charge goes away. And that negative plate on capacitor 3 is going to become negative 7.68. Capacitor 4, the positive plate, is going to become 2.88. That's a difference of 4.80 microcoulombs. Now, what happened was, if you think of what flowed here, that amount of charge flowed from B to A. So if we're thinking in terms of positive charge, it flowed from B to A, but you know, this is a circuit with electrons flowing. It's probably more sensible to think in terms of the flow rate of negative charge, and that would require that electrons traveling from point A to B came in and provided the negative charge, this one right here, negative 7.68 compared with the 2.88. Anyway, we can take that difference and that becomes the charge. So this problem is not an RC circuit. It's not showing the charging process or the discharging process. Instead, what it's doing is it's checking your understanding about how charge is conserved in the capacitors, and that we have to be able to account for where the charge has gone when we've charged these capacitors initially to where we've closed the switch, and now they're charged with different amounts than they were before. Okay. Anyway, I thought this was a good set of problems. I hope these have been useful, kind of, talking through some of these problems, thinking about what's been going on in these chapters. Any questions? Stop by and we will take a look at those.